Hello viewers, welcome to online course on Mathematics 3. This course basically for undergraduate student or BTech student of engineering field. Today we are going to discuss about the fundamental theorem of arithmetic in the module Number Theory of Mathematics 3. Myself Sanjay Vishwas, Assistant Professor of Mathematics of Department of Applied Science and Humanities of Guru Nanak Institute of Technology. Here is my details of contact information. If you are facing any kind of problem regarding my online class, you can call me or send message through my mail ID sanjay.vishwas@gnit.ac.in. Before we start today's lecture, let's quickly recall the last lecture. So in the last lecture we have discussed about the divisibility and division algorithm. So in this lecture we have discussed about the introduction of divisibility, and after that we have talked about some properties of divisibility, and then we have talked about the division algorithm as well. Then we have discussed some theorem on divisibility, and after that we have talked about some examples on divisibility and division algorithm on number theory. Today we are going to discuss about the fundamental theorem of arithmetic. This is my third lecture on the module 3, that means in the number theory of mathematics 3. So here is the content of today's lecture. At first we will discuss about the prime numbers, so definition of prime numbers and some theorem on prime numbers, and after that we will talk about the Euclid theorem on number theory, and after that we will study on the fundamental theorem of arithmetic. So in that section we will discuss the statement and the proof of the fundamental theorem of arithmetic, and after that we will discuss about some theorem on fundamental theorem of arithmetic, and after that we will discuss some related examples on fundamental theorem of arithmetic. So this is the content of today's lecture. So at first we will discuss about the prime numbers and some related examples on prime number. Then we will discuss about the Euclid's theorem, and after that we will talk about the fundamental theorem of arithmetic, and some related theorem and examples we will discuss in lecture 3. So let us begin with the introduction to prime numbers. So here is the definition of prime numbers. So a positive integer p is greater than 1 is called the prime if the only positive factors of p are 1 and p. Okay, so if a positive integer greater than 1 is not prime, then n is called the composite number. And you know that the composite number is a multiple of prime numbers. Okay, so here is the note on the prime numbers. So the positive integer 1 is neither a prime or composite number, and any composite number is divisible by 2, you know that. So the positive integer 1 is neither a prime number nor a composite number. The only even prime integer, it is 2. Okay, so 2 is the first as well as even prime numbers, and rest of the prime numbers are odd. So only 2 is the prime number and it is the even prime number, and other prime numbers, they are all odd numbers. And if n is a composite, then there exists a positive integer a and b such that n is equal to a into b. Okay, and a and b is lies in 1 to n. So that means 1 less than a less than n and 1 less than b less than n. So that means a and b lies in the interval 1 to n, or and in between 1 and n. Okay, so the composite number is of the form n into a into b, where n be the composite number and a b be any two positive integers. Okay, and this is lies in that interval, that means 1 to n. Okay, so here is the example of the prime numbers. The integer 2, 3, 5, 7, etc. are the prime numbers. Okay, so this number are all greater than 1, and you know that 2 is the first prime number and it is even, and all other prime numbers they are odd. So 3 is the prime number, so it cannot be written as n is equal to a into b. Okay, 5 cannot be written as a into b, as well as 7 cannot be written as a into b. So these are all the prime numbers, not a composite number. But where 4, 6, 9, 10, etc. are the composite number, because 4 can be written as 2 into 2. Okay, where 2 is a number is lies in 1 to 4, as well as 6 it is equals to 3 into 2, where 3 and 2 are the numbers lies in 1 to 6. Okay, 9 is the number and it can be written as 3 into 3, and 3 is lies in the interval 1 to 9, and 10 is the number, it is equals to 5 into 2, and 2 and 5 both the numbers are lies in 1 to 10. So these numbers, that means 4, 6, 9, 10, okay, etc. This number are the composite number, and it can be written as n is equal to a into b, where a, b, b2 numbers or positive integers lies in the interval 1 to n. Let us move on the next slide. So in this slide we will discuss about the theorem on prime numbers. So here is the theorem. This is the first theorem on prime numbers. An integer n greater than or equals to 2 is composite. That means it can be written as n is equal to a into b if and only if it has a factors a and b such that 1 less than a less than n, that means a is lies in 1 to n, and as well as b is lies in 1 to n. This is the theorem. The necessary part of this theorem is that if n greater than or equals to 2 is a composite number, then there is a factor a and b such that a and b lies in the interval 1 to n. Let n greater than or equals to 2, then if direction is obvious, so that is the necessary part is obvious, and any composite number can be written as n is equal to a into b, where a, b and b two numbers lies in the interval a to n. Okay, so for the only if, that means the sufficient part of the above theorem, assume that n is a composite number. Okay, so n is a composite number, then it has a positive integer factor a such that a is not equals to 1 and a is not equals to n. That means a is lies in that interval, and this means that there is AB, so ABB number such that n is equal to a into b, and since n and a are the positive numbers, so that b is also a positive number, where a is a positive number, ab a positive number. So, and you know that n is equal to a into b, so any two positive number, that means the multiplication of any two positive number, it is a positive number. So therefore b is also a positive number. Hence 1 is less or equal to a and 1 is less or equal to b. So these two numbers are greater than or equals to 1. That means these two are positive numbers. So by the properties of divisibility, we have a is less or equal to n and b is less or equal to n, and since a is not equals to 1 and a is not equals to n, so we have a is lies in 1 to n, that means 1 less than a less than n, and if b is equal to 1, then from this equation we will get a is equal to n, and it is not possible. So therefore b is not equals to 1, as well as if b is equal to n, then a is equal to 1. If we put b is equal to n in that equation, we will get a is equal to 1, and which is also not possible. So b is also lies in the interval 1 to n, that means 1 less than b less than n. So this is the sufficient part of the above theorem. So now move on the second theorem on the prime numbers. In n greater than 1, then there exists a prime p such that p divides n. This is the theorem. So here is the proof of the above theorem. let S denote the set of all integers greater than 1 and that have no prime divisor. So we must show that S is empty. Okay. So from this we will show that S is an empty set. So if S is not empty, then by the well ordering principle or the well ordering property, it has a smallest number, call it M, and now M is greater than 1 and has no prime divisor. So then M cannot be prime. As you know, every number is a divisor of itself. Okay, so M cannot be a prime number. So hence M is a composite number. So if either any number it is not prime, then it is composite number. Okay. So therefore by the previous theorem, M is equal to A into B. So any composite number can be written as a multiple of two numbers. Okay. So the two numbers will be A and B, and where A and B is lies in the interval 1 and n. That means 1 less than A less than M and 1 less than B less than M. And since 1 less than A less than M, then the factor A is not a member of X. So A must be a prime divisor of P. So then P divides A. Okay, this is the prime divisor of P. So P divides A. And A divides M. So by the properties of the divisibility we have. So from this we will get P divides M, and this is a contradiction by our assumption that M has no prime divisor. So the set S must be empty. So this is the second theorem of prime numbers. So now move on the next theorem, and this is called the Euclid's first theorem. Okay, so here is the theorem. The number of prime numbers is infinity. This is called the Euclid first theorem. So here is the proof of the above theorem. If possible, let the number of prime be finite and b it is equals to n. So let them be arranged as p1, p2 up to pn, and then form the number n is equal to 1 plus p1 into p2 and up to pn, where p1, p2, p3 up to pn they are the prime numbers. Okay, and now no one of these is a divisor of n. When n can be written as this, then p1 does not divide n, p2 does not divide n, up to pn does not divide n. So n is either a prime, it is greater than pn, or has a prime greater than pn as a factor. But this contradicts our assumption that Pn is a greatest prime. So hence the number of prime is infinity. Okay, this is the proof of the above theorem. So now move on the next theorem, and the proposition of Euclid's first theorem. Okay, so here is the theorem on the proposition of Euclid's first theorem. If n is greater than 1 is a composite integer, then there exists a prime p such that p divides n and p is lesser equal to root over of n. This is the theorem. Okay, so here is the proof of the above theorem. Since n is greater than 1 is a composite integer and n can be written as, you know that any composite number can be expressed as n is equal to a into b. Okay, so where a and b both are the numbers lies in the interval 1 to n, and here a is lesser or equal to b. So that means 1 less than a lesser or equal to b less than a. And let us consider a is lesser or equal to root over of a, and if it is not true, then a is greater than root over of a. Okay, so you know a dot a, it is greater than root over of a into root over of n, and this implies, and where you know a is greater than root over of n, b is also root over of n, so multiple of a into b it is greater than root n into root n. Therefore ab is greater than n, and which is a contradiction. So where you know n is a composite number and is equals to n. So, but here AB is greater than n, so which is a contradiction. So, by the fundamental theorem, either A is a prime or has a prime divisor P. So, therefore, P is devised n and P is less or equal to root over of n. Okay, this is the proof of the above theorem. When we put A is greater than root n, then the above theorem is not true. That means there is a contradiction, but AB is greater than n. But we know that any composite number can be written as n is equal to a into b. But when we put a greater than root n, then from this we will get AB is greater than n. Okay, so the theorem is not true. Therefore, by the fundamental theorem, either A is a prime or it has a prime divisor P. So that means P divides n and P less or equal to root over of n. So this is the proof of the above theorem. So here is the note on the above theorem. To check a given integer n is prime, it is sufficient to see that it is not divisible by any prime less than or equal to its square root. Okay, this is a very important part of the prime numbers. So now move on the next theorem on proposition of Euclid's first theorem. So here is the theorem, and this is called the Euclid's argument. Okay, so let P is belongs to Z. So P be the number, and this is the integer, and P is greater or equals to 2. Then P is prime if and only if P divised AB implies P divised A or P divised B, where AB be two numbers, there belongs to capital N. That means AB be two natural numbers. So here is the proof of the above theorem. Given that A divides B, so that means A is either 1 or A is equal to P, because P is a prime number. So either A is equal to 1 or A is equal to P. Otherwise it is not divisible by A of the number P. And suppose that P divides AB. And from this we will prove that either P divides A or P divides B. So then there exists a number K, it is belongs to N. So N be the set of natural number, you know, such that K into P it is equals to AB. This is the definition of the divisibility. Okay, so from definition we will get this one. AB is equal to K into P, where K be any number, it is belongs to N. And suppose that P does not divide A, that means GCD of AB it is equals to 1. Where P does not divide A, that means they are relatively prime, so their GCD is equal to 1. So that means GCD of A comma P it is equals to 1. So thus there exists two integer x, y, it is belongs to Z, such that x into A plus y into P it is equals to 1. So this is the properties of the greatest common divisor. You know that xa plus yp it is equals to 1, but GCD of AP is equal to 1. So now multiplying by B on both sides, from the above equation we will get x AB plus y PB it is equals to B. Okay, and you know that AB is equal to K into P. Now substituting KB for the number AB we will get x KP plus y PB it is equals to B. Now taking P as common from the left of the above equation we will get xk plus yb into P it is equals to B. So that means P divides B. Okay. So P divides AB, and this implies P divides B when P does not divide A. And similarly, when P does not divide B, then from above, that means P divides AB and it is implies P divised A. Okay, this is the necessary part of the above theorem. And conversely, given that P divised AB and it's imply P divised A or P divised B. So, and from this we will prove that P be a prime numbers. Okay, so suppose that A divides B. So then there exists a number k and k belongs to n, where n be any natural number such that ak is equal to b. This is the definition of the divisibility. Okay, so you know when a divides b, then it can be written as ak is equal to b, where a is less than b. You know that, and so p divides ak, and from the above we will get either p divides k or p divides k. And if you know P divides A, then from the divisibility theorem we will get P into L, it is equals to A for some L belongs to capital L, where N be any natural number. Okay, so in which case, that means when we put P is equal to AK in the above equation, we will get AKL, it is equals to A. And after cancelling the term A on both sides, we will get KL is equal to 1, and which implies that K is equal to 1. So therefore, from this equation, that is AK is equal to P, we will get K is equal to P. And if P divides K, then from the division algorithm, we will get from this K is equal to P into M for some M belongs to M. And you know, now multiplying by A on both sides of this equation, we will get AMP, it is equals to A into K, and then substituting AK is equal to P in the above equation, we will get AMP, it is equals to P, where first of all we will multiply by A on both sides of the above equation, we will get KA is equal to PMA, and you know that Ka, it is equals to P, so and substituting P for AK in the above equation, we will get AMP, it is equals to P, and after cancelling the term P on both, we will get AM is equal to 1, and which implies that A is equal to 1. So that means when A divide P, then A is either P or A is equal to 1. So that means P is a prime number. Hence the proof of the sufficient part of the above theorem. And after that we will discuss about the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic states that every natural number greater than 1 is either a prime or a product of a finite number of prime. And this factorization is unique except for the arrangement of the factors. Before we prove this fundamental fact, it is important to realize that not all set of numbers have these properties. Okay, so the fundamental theorem of arithmetic, it is actually every natural number greater than 1, it is either a prime number or a product of a finite number of primes. Okay, this is called the fundamental property of arithmetic. So where unique factorization fail. So for example, let us consider the set of even integers, namely e is equal to 2 into k, such that k belongs to z. Okay, so k be any integer and 2k be the even integer. That means plus minus 2, plus minus 4, plus minus 6, plus minus 8, 4. These are the even integers. We can add, subtract, even multiply elements of E and obtain the elements, and these are all in E. That means multiply of 2 even integer, it is even. Subtract of 2 even integer, it is even. And addition of 2 integer, it is equals to the even integer. So we can add, subtract or multiply any numbers of E, and from this we will obtain a numbers, and it belongs to E. So we say that the set E is closed under addition or subtraction or multiplication. But in a division it is not possible. So however, this is not the set of integers, so we should define what we mean by divisibility. So namely, for any two elements of E, we say A divides B, and that means there exists a number M and it belongs to E such that B is equal to M into A. Okay, so this importance of M, it is belongs to E, and it should not be the overload. So for example, 2 divides 8, that means 8 it is equal to M into 2, but M is equal to 4 and it belongs to E. It is possible. But 2 does not divide 6 because there is no number M it is belongs to E such that 6 is equal to M into 2. So in that case where M is equal to 3 and 3 is not belongs to E. So what are the same prime in E? So for example, 2 is a prime in E because there does not exist N and M in E such that 2 is equal to N into M. Similarly, 6 is a prime in E because there does not exist NM in E such that 6 is equal to N into M. Also 10, 13, they are all prime numbers in E, and so 60, it is equals to 2 into 30 is not. So however, since 60 is equal to 10 into 6, and we conclude that the unique factorization into prime in E is not unique. So here is the above theorem is failed. So set of all even integers, but the function is not unique. And after that we will discuss about the characterization of the prime numbers. So before getting the fundamental theorem of arithmetic, we need an important result. So there are some result on characterization of prime numbers. So the first lemma is the prime characterization. So a natural number P is a prime if and only if P divides BC implies P divides B or P divides C for any natural numbers B and C. This is called the prime characterization. This is the lemma of characterization of prime numbers. So now move on the next theorem or fundamental theorem of arithmetics. And this is the third theorem. It is called the fundamental theorem of arithmetic. So for any integer greater than 1 can be expressed as a product of prime in a unique way apart from the order of the prime factors. And this is called the fundamental theorem of arithmetic. So here is the proof of the above theorem. So the existence of such a factorization is proved by induction. So assume that every integer less than n can be written as a product of primes, and if n is prime, then we have a factorization of n consisting of 1 prime factors. So if a prime, then it is either 1 or this number, or it is either 1 or itself. So if n is a composite number, then n can be written as n1 into n2. But n1 and n2 be two numbers and they are lies in 1 to n. That means 1 less than n1 less than n as well as 1 less than n2 less than n. And it follows from the induction hypothesis that each of n1 and n2 are the product of primes. Now suppose that there is an integer with two different factorizations. So you know, this is the fundamental theorem. You know, for any integer n greater than 1 can be expressed as a product of primes, and this primes is unique. So that means suppose that there exists an integer with two different factorizations. So then there is a list such number n, then n is equal to say p1, p2 up to pr. It is equal to q1, q2 up to qs. So there are two different factorizations, but from this we will prove that the factorization is unique. So where each pi and qj is a prime, and where the two factorizations are different. Since p1 divides the product q1 q2 up to qs, then it follows that p1 divides one of the prime numbers q1 q2 up to qs. And this is the fundamental property of divisibility. And remembering these numbers, we may assume that p1 divides q1. Okay, so either p1 divides q1 or p1 divides q2 or p1 divides q3 and up to p1 divides qs. So we assume that p1 divides q1, and which of course means that p1 is equal to q1. And dividing in by q1, we get the similar result. Okay, so therefore n divides p1, it is equals to p1 q2 up to pn, or q1 q2 up to qs. So with two different prime factorization, but this would contradict the assumption that n is the smallest number with different factorization. Okay, so therefore, if the prime factorization of two given numbers are known, then we can easily determine their greatest common divisor or least common multiplier, that is GCD or LCM. So here is the example of the above theorem. So sum of the prime in the product may be equal. So for instance 12, and 12 can be written as 2 into 2 into 3. These are the factors of 12. It can be written as 2 to the power 2 into 3. Okay, so the fundamental theorem is sometimes stated as every numbers greater than 1 can be factorized uniquely as a product of powers of prime. For example, say 600, and 600 can be written as 2 into 2 into 2 into 3 into 5 into 5. They are the factors of 600, and it can be written as 2 to the power 3 into 3 into 5 to the power 2. Okay, so we will break the proof of the fundamental theorem into a sequence of numbers. So these are the examples of the fundamental theorem of arithmetics. So now move on the existence of fundamental theorem of arithmetic. So here is the lemma or the theorem of existence of the fundamental theorem of arithmetic. So if n greater than 1, then there exists prime p1 p2 up to ps where s greater or equals to 1 such that n is equal to p1 p2 up to ps, and p1 is less or equal to p2 and less or equal to ps. That means the prime numbers they are in ascending order. So here is the proof of the existence of the fundamental theorem of arithmetic. So we will use induction on n. So the base step, it is and there are two steps in mathematical induction. The first step, it is the base step, and the second step, it is the inductive step. Okay, so first of all, we use the base step. That means when we put n is equal to 2 in that case, and since 2 is a prime, so we can take s is equal to 1 and p1 is equal to 2. So for the inductive step, assume that the hypothesis that the lemma hold for 2 less or equal to n less or equal to k. So this the above lemma, it is holding in that interval. That means 2 to k. And we will show that it holds for k plus 1. And this is the mathematical induction. And if k plus 1 is prime, then s is equal to 1 and p1 is equal to k plus 1. And k plus 1 is a composite, then we write k plus 1 is equal to a into b. When it is a composite number, then it can be written as a into b, where a and b be two numbers lies in the interval 1 to k plus 1. That means 1 less than a less than k plus 1 as well as 1 less than b less than k plus 1. So by the induction hypothesis, there are primes p1, p2 up to pu and q1, q2 up to qp such that a is equal to, so k plus 1 be the composite number, it can be written as a into b, and where a and b be the numbers and a is equal to product of primes, that means P1, P2 up to Pu, and P with another number, it is also the product of primes, that means Q1, Q2 up to Qp. And this gives that K plus 1 is a product of prime numbers, while A is the product of primes, that means P1, P2 up to Pu, and P with another number, it is also the product of primes, that means Q1, Q2 up to Qp. So K plus 1, it is equals to P1, P2 up to Pu into Q1, Q2 up to Qp. So where S is equal to E plus P. And now reorder the primes into ascending order if it is necessary. Then the base step and the inductive step together gives that the statement is true for all n greater than 1. This is the existence of the fundamental theorem of arithmetic. So now move on the uniqueness of the fundamental theorem of arithmetic. So if n it is equals to P1, P2 up to Ps, where S is greater or equals to 1 and P1 less or equal to P2 and up to Ps. Okay, that means the factors P1, P2 are all in ascending order, and also n is equal to Q1, Q2 up to Qt for t greater or equals to 1 with Q1 less or equal to Q2 less or equal to and up to less or equal to Qt. That means Q1, Q2, these numbers are the primes, they are in ascending order, where t greater or equals to S and Pi is equal to Qi for all high between 1 and S. This is the uniqueness of the fundamental theorem of arithmetic. So here is the proof of the theorem. The proof is by the induction on S. So in case S is equal to 1, this is the best case of the mathematical induction. So when we put n is equal to P1, it is a prime, and we have P1 is equals to Q1, Q2 up to Qt. Now t must be 1 or else, and this is a factorization of the prime P1, and therefore P1 is equal to Q1. So this is given. When we put I is equal to 1, we will get this one. Okay, this is the base case. Now move on the inductive case of mathematical induction. So now assume that the inductive hypothesis that the result holds for all S, and S lies in the interval 0 to k. That means 1 less or equal to S less or equal to k. So we must show that the result holds for S is equal to k plus 1. So assume that n is equal to P1, P2 up to Pk into Pk plus 1, where P1 less or equal to P2 less or equal to P3 and up to less or equal to Pk plus 1. And also n is equal to, you know that Q1, Q2 up to Qt, and this is the given, and where Q1 less or equal to Q2 and up to less or equal to Qt. So the numbers are in ascending order. So clearly Pk plus 1 is divides n. So these are the prime numbers. It is the factor of n. So and any of this number is divides n. So here Pk plus 1 is divides n. So Pk plus 1 is divide Q1 Q2 up to Q2, where you know Kn is equal to Q1 Q2 up to Q2. Now from the implied lemma, it gives that Pk plus 1 divides some Qis, and that means Pk plus 1 it is equals to Qi, or else Pk plus 1 would be a non-one divisor of the prime Qi, and which is impossible. Okay, so that means Pk plus 1 it is equals to Qi, and it is less than Qt, you know that. And similar argument shows that Qt is equal to Pj, you know, and Pj it is less or equal to Pk plus 1. So therefore Pk plus 1 is equals to Qt. So therefore cancel Pk plus 1 is equal to Qt. From the two sides of the above equation we will get P1, P2 up to Pk into Pk plus 1, it is equals to Q1, Q2 up to Qt. And now the induction hypothesis appeals k is equal to t minus 1 and pi is equal to qi, that is given for I is equal to 1 to up to t minus 1. So the lemma hold also in the s is equal to k plus 1 case. So by the mathematical induction, it is hold for all s greater equals to 1. And this is the proof of the uniqueness of the fundamental theorem of arithmetic. So here is the example of the above theorem. So unique factorization gives an alternative and conceptually simpler way to find the greatest common divisor of two integers or two numbers. For example, 600. And it can be written as, you know, this is the factor of the primes, and it can be written as 2 to the power 3 into 3 to the power 1 into 5 to the power 2 into 7 to the power 0, 52, and it can be written as the product of prime factor, that means 2 to the power 2 into 3 to the power 2 into 5 to the power 0 into 7 to the power 1. Now 2 to the power 2 divides both numbers. So does 3 to the power 1, it is divides both numbers, that means 600 as well as 252. But 3 to the power 2 does not divide both. Okay, so 3 to the power 2 divide 252, but it is not divide 600. As well as 3 to the power 2 divide both numbers, but 2 to the power 3 does not divide 252. As well as the highest power of 5 divides both numbers is 5 to the power 0. And similarly, the highest power of 7 that work for both, that means divide both numbers, that means 600 as well as 256, and it is 7 to the power 0. So the GCD of 600 and 252, it is equals to 2 to the power 2 into 3 to the power 1 into 5 to the power 0 into 7 to the power 0. That means 2 to the power 2, it is divide both the numbers, 3 to the power 1 divide both the numbers, 5 to the power 0 it is divide both the numbers, that means 600 and 252 as well as 7 to the power 0. So GCD of 600 and 252, it is equals to 2 to the power 2 into 3 to the power 1 into 5 to the power 0 into 7 to the power 0, that means 24. So 24 is the common divisor of 600 and 252. So in general, we can find the greatest common divisor of two numbers factoring, then taking the minimum power of 2 times the minimum power of 3, etc. So now move on the next slide. So in this slide, we will discuss about the application of the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic, it is an integral pillar of number theory, especially due to its extensive application in various contexts. So the basic idea of the theorem is that any integer greater than 1 is either prime or it can be expressed as a product of prime factorizations. You know that this is the fundamental theorem of arithmetic. So as such, we can explore this concept to make work easier when we want to find the greatest common divisor of a numbers, or even the least common multiplier. So this is the LCM and this one is the GCD of a numbers. So the theorem allows us to express the given number as a product of its prime factors, and hence making it easy to establish the greatest common divisor or the least common multiplier. So from first of all, we will take this number as a multiple of prime factors, and after that from this we will get the greatest common divisor as well as the least common multiplier of the above numbers. So here is the example of the fundamental theorem of arithmetic. So that there are infinitely many primes of the form 4n plus 3. This is the example. So here is the solution of the above theorem. So first notice that the product of any two natural numbers of the form 4n plus 1 and also has the form 4n plus 1, and which can be seen by letting a is equal to 4s plus 1 and b is equal to 4n plus 1, variation of the two natural numbers. Okay, so then AB can be written as 4s plus 1 into 4r plus 1. And after simplifying this factor, we will get 16 rs plus 4r plus 4s plus 1. and after taking 4 as common from the first 3 terms, you will get 4 into 4rs plus r plus s plus 1, and this is equals to 4 into k plus 1, where k is equal to 4 rs plus r plus s. This is the integer. So therefore, we assume there are only a finite number of primes of the form 4k plus 3, and say p0 is equal to 3. Okay, so p1, p2 up to pn is all of them, and we consider the natural numbers q, and it is equals to 4 into p1, p2 up to pn plus 3. Okay, so where p1, p2 up to pn, they are all the prime numbers. So notice that the prime factorization of q, namely q, it is equals to q1, q2, q2 and up to qm must contain at least one prime of the form 4k plus 3. Okay, so there exists at least one prime numbers, and it is of the form this 4k plus 3, because otherwise q would be the form 4k plus 1. Either it is form 4k plus 3 or 4k plus 1. So thus there is one prime in the prime factorization of q that is of the form 4k plus 3, say qt. Okay, and either qt is equal to 3 or qt greater than 3. So if qt is equal to 3, then 3 divides q, and which means that 3 divides q minus 3 as well, and also 3 divised, so that means 3 divides q minus 3, that means it implies 3 divides 4 into p1, p2 up to pn, and which is observed. And if qt is greater than 3, then qt is equal to pj for some j in between 1 to n, and so qt divised q, and it is implies qt divised q minus 4 into p1, p2 up to pn, and it is equals to 3, and which is also observed. So therefore there are infinitely many primes of the form 4n plus 3. This is the proof of the above examples. I will stop here today's lecture. Thank you.